What I've got on the screen here is a contour plot for the function that we worked with in the last video, that 3x minus x cubed minus 2y squared plus y to the fourth. I generated this using Wolfram Alpha. Just so you know, on Wolfram Alpha, all you do is literally type the words contour plot 4 and then the formula for your function, and Wolfram Alpha will generate something like this picture. Now, I've added to the picture. Wolfram Alpha will draw the level curves, but it won't label them. So I went in and did a few calculations so I was able to label these level curves so that we could do an analysis a little bit better. Over here on the right, I've got this table where I list our 6 critical points and the classifications that we got for them using the second partials test. I do just want to emphasize, we didn't say that 1, 0 was a max. We said it was the location of a max. I just didn't have enough room on the screen to write location 6 times. Okay. So let's start by taking a look at the point 1, 0. That's this point right here, and we had determined that it was a max. Now, maxes and mins are going to look pretty similar on a contour plot. Anytime you've got a completely enclosed curve like this, generally speaking, if Wolfram Alpha had drawn more level curves, there would be a shrinking sequence of curves that were approaching this point right here, which is our max. And if you've got a shrinking sequence of completely closed curves, that's going to be a max or a min. To see which it is, you just sort of follow the arrow. As we approach that point, you can see our z-values were going -1, 0, 1, 2. That looks like increasing to me, so that's why that particular point is a max. Now, if we look at our 2 mins, those were here at -1, 1, and here at -1, -1. Both of those, without the labels, look very similar to the max. They're both points that are enclosed in these closed loops. But now, if you follow the level curves towards that point, you can see we're going from a level curve for 0 to -1 to -2 to -3. Now we're decreasing, so that's going to be a min. All right, let's take a look at a saddle. Let's take a look at the point 1, 1, which is right here. Now for the saddle, you can see that the level curve for 1 crosses itself. That's part of the level curve for 1. And this is also part of the level curve for 1. So it crosses itself there, and that's generally what I can expect to see on a saddle. Now, if I go through the point 1, 1 on that level curve, my z-value isn't changing. It's just 1. But I should be able to find 2 different paths through the point 1, 1, where along one of the paths that's going to be a min, and along one it's a max. If I take a look at this path here that passes through this point, 1, 1, you can see I was at a z-value of 2, then 1, then I'm going back towards 2. Along that particular path, this was the location of a min. But if I come along this path that also passes through that point, my z-values are increasing until I hit 1, and then they start decreasing again. And so along that particular path, we had a max. And that's actually true at the other saddle points that we have here and here. Whoops, meant that to be an arrow, here and here. Okay, at these saddles, you should be able to find one path that passes through that point, where that point's going to be the location of a max, and one point where it's going to be the location of a min. So generally speaking, maxes and mins, at least if they occur at isolated points, those are going to be inside a sequence of increasingly smaller closed curves. Saddle points are going to be where a single level curve for a single z-value intersects itself at some point. Okay, so that's kind of nice to know. There are some questions in the homework that give you contour plots, and that also can help you in interpreting contour plots if you're working with them in other problems.